Great. So let's talk about what it takes to go from having a prototype of a device to something that can actually be produced. Um, you've got a prototype. You've probably put it together by hand. You've got 3D printed parts. You've made one or two. Um, there's a few more steps that are needed to go from here to actually having a product that you can produce. We're going to talk about some of those things here. I will say that one of the important things to consider at this stage is, have I made the right product? And that's a matter of really circling back to understand the unmet need that you're trying to fill in the marketplace. So do we really have a good understanding of the market requirements, and have we designed a product that clearly fits those requirements and will be successful? People have lots of great ideas all the time and create lots of what you might think are pretty cool products or pretty nifty technologies, but if they don't actually solve a problem that someone's willing to spend money for a solution, it's just not going to work. So let's just say this is an important place to double check on that before you get into the significant effort, because it takes a lot to go from prototype into a production device. Some of the questions, how about cost? There's lots of ways to build a product. The challenge is figuring out how to build it in a way that is most cost effective. You got to think about how it's going to be manufactured, and can it be? When we prototype things, there are things we can do with 3D printing, for example, that you can't do with mass production technologies. How about reliability? Manufacturing introduces all kinds of variabilities that you can't even imagine when you've just made a prototype, and you've got to think about how those variabilities are going to affect the reliability of your device. And then there's typically testing that has to be done. So we think about design for manufacturing, but we also think about design for cost, design for assembly, design for reliability, all these different things. And typically in the industry, people will use the terminology DFX, or design for X, design for all of those different perspectives. Let's talk about some of those. At the end of the day, really, what we call DFX, it's just good design in the first place, because most of these issues are things you consider early in the design process. It's around understanding those requirements, like we talked a minute ago. Do we really understand the market needs, and have we designed a product to meet those needs? It's about thinking about design from the standpoint of simplicity, about combining parts or functions where possible. Fewer parts means lower cost, generally speaking. So that's an important design philosophy. Trading off complexity of a part versus complexity of assembly. There's components that you could design that might combine a couple of things so that you just have one part to make. That might make assembly easier, but you have a more complex part. That's going to cost more. So you got to think through that. Think through how you're going to manufacture all of the pieces and parts and assemble them. Thinking through the optimal manufacturing processes, and then designing with that in mind. And then thinking through how you're going to control the quality of all those parts in the finished product, and how to make sure that you produce something that's going to be suitably reliable. So in the case of the device that you guys have prototyped, you have a trigger that causes that device to make a sound. Well, how reliable is that trigger? Is there a threshold that you've designed to above which it'll trigger, below which it won't? What things might contribute to variability in that trigger level that's going to cause that device to work sometimes and maybe not work other times? You got to think about how all those the various design elements contribute to that reliability. When we think about design for manufacturing, assembly, reliability, etc., There's a lot of tools that we use in the commercial development process to analyze parts as you design them. What you're looking at on the one side of the screen here is part of an enclosure for a medical computer monitor arm, actually. This is one molded part, and you see sort of behind it a detailed engineering drawing for that part. Designing a part to be injection molded as this one is, there's a lot of thinking that goes into that part. You might ask what you might be thinking about what the red and blue shading represents on that representation of a CAD model. That's actually an analysis that we do around mold parting. So this component is made in an injection mold where the mold has two halves that come together. It gets filled with a high temperature liquid polymer. The part cools and the halves of the mold pull apart. And so this is representative of what's called a parting analysis. So the red is the half of the mold that pulls away to one side. The green represents the other half of the mold that pulls away to the other side. And you look at the way in which those two halves pull apart to make sure there's no interferences, that those halves can pull apart cleanly without damage to any of the features that are intended to be molded there. We'll talk a little bit more just briefly about assigning tolerances to dimensions, but you see a lot of symbology on that detailed drawing in the background there that represent critical design features in this part and controls that are being specified through that symbology that represents tolerances and important controls that the manufacturer would apply in making that part. You've got to think about different manufacturing processes. We'll talk a little bit more about that. And then throughout this whole effort, there's important subject matter expertise from different perspectives that you need to bring in, from mechanical engineering, electronics, packaging, manufacturing processes. So I'll talk briefly about cost. Usually when we're building a prototype, we may have a cost budget for the parts that we use, but we're not really thinking about making that device at a cost that is necessary for a business to be commercially viable. And it's typically the case that prototypes may cost thousands of dollars to make just one, but a product's got to cost less than, let's say, $50 in order to be commercially viable in the marketplace. So this is actually a significant amount of effort in the commercial world that goes into thinking about how to optimize the cost for a device. And there's strategies to do this. There's what I call the Walmart strategy, which is you find your suppliers and you beat them up to get the lowest prices you possibly can. You buy at at enormous volumes to get volume discounts and so forth. And that's a strategy that people use commercially in product development as well. And you can get a little bit from that, but you can actually get more benefit by sort of revisiting what I call the system architecture, the decisions that were made in architecting the design of the system. And there's things you can do there in terms of looking at part count and looking at ways to combine functionality into a smaller number of parts, really understanding the design margin, whether that's in the design of a battery. If you have a battery-powered device, does the battery need to last for a day, but we've selected a battery that's going to last a week? What's the use case there in terms of how the customer is going to use the device and recharge the battery and things of that nature? So you'll look at margin. And then, what are the performance requirements? Again, with the battery, if we've worked on things where initially a battery was designed to last for a week, but thinking about, again, going back to the use case, is it going to be typical for a customer to use a device for one shift of operation and then set it in a charging station overnight? Maybe it doesn't need to last a week. So that's what I mean by loosening performance requirements around, in that example, battery life. Another element of cost optimization is what people call make versus buy. So there are things that you can make yourself or have made for you versus buying, off-the-shelf components. And you can see, I won't go through all these details, but people think about these different attributes and pros and cons of make versus buy as you make these decisions. And I'll take two extremes. Microprocessors, for example, you're not going to make your own microprocessor because the cost to make the factory to make the microprocessor is prohibitive. But you might make your own molded plastic parts. Quick example: we worked on a essentially robotic camera system that tracks a wireless tag. So this camera automatically tracks a wireless tag that, for example, someone might wear, and the camera tracks and captures video. So commercial product going to be made in the many thousands, has a number of plastic gears to work the drivetrain of this device. And you can buy plastic gears for a couple of bucks a piece, but when we did the analysis of making many thousands of units versus cost, we concluded, we could actually make these plastic gears less expensive ourselves versus buying them off the shelf from an existing supplier. So those are the kinds of things that people think about in that regard. Production methods, as we think about cost and getting a device into production, there's a lot of choices to be made. People use 3D printing, as you guys have, to make enclosures for your device. It's ubiquitous, it's easy. If you're going to be thinking about taking a device into commercial production at a scale of hundreds or thousands or many thousands, lots of other opportunities present themselves. And we've identified a couple of typical production methods here with some attributes to think about and some rankings in terms of capabilities. An interesting one for lower volume production of polymer parts that often people are not necessarily aware of is this urethane casting, which is interesting. You take a 3D printed part, you pour a 2-part liquid urethane polymer over that part, you split that in half, and now you've got a urethane cast, basically, that you can use to then fill with a casting polymer type of a solution to manufacture plastic parts. Injection molding, there's lots of, I'll say, flavors of injection molding as you get into the details that are suitable for different quantities of parts. But suffice it to say, there are many different ways of manufacturing mechanical components, each of which have pros and cons around different attributes. And the key from a product design impact is to understand the constraints and limitations of these different production methods, ideally in the design process, so that when you get to a point where you're ready to scale up, you've thought about how to manufacture your device. A couple of considerations that play into mechanical components as you design the details for manufacturing. I've taken two fairly simple examples out of many dozens of issues that one typically needs to consider, but how things fit together, fits and tolerances is one. example of an issue that seems pretty simple, but it actually gets really complicated, particularly as assemblies get more complicated. But the issue is this: everything in a product gets put together, and we've got to think about different parts and the tolerances on the mechanical dimensions of these parts. So if you look at this example, which is a shaft that is fitting into a hole, the graphic there illustrates clearances, and the orange pieces, the orange elements there show the range of size of the shaft fitting into the bore that you may experience given the tolerances on those components. And those have to be specified to make sure things fit together as you expect. Now, if you think about something like the enclosure for the devices that you've been working on, it probably has a couple of pieces that have to fit together. Maybe that enclosure comes together a top and bottom or front and back, and we've got to think about the tolerances of how those two halves fit. When you think about something more complex, like say a smartphone, you have the same thing, plus tolerances around all of the internal components. You know, when we design complex electromechanical devices or electronics, we even put tolerances on the size of batteries and circuit boards and those electronic things to make sure they all fit together in a compact package. So that gets really complicated, and people talk about the stack up of tolerances. So again, in a smartphone, you've got, you know, the front and the back of the enclosures, you've got buttons and switches, you've got batteries and circuit boards inside, an LCD screen. Someone has done the analysis of all the tolerances on all those different parts to make sure that when that phone is assembled, all those pieces and parts can actually go together within that assembly. Very complex. You see on the other side of this chart some of the things that people think about for design of molded plastic parts. At the top, that graphic illustrates just the fact that when this high temperature polymer cools, if I have different thicknesses, elements of that part are going to cool at different rates, and that can cause that sink mark that's shown there as an example. So that's just one of, you know, many dozens of things people think about in terms of designing parts for injection molding. Draft is another one. The two halves of the mold can't pull apart if there's not what's called draft, which is specified as an angle. So if you see that little chart, 1 degree of draft is typical to enable the two halves of the mold to come apart. At 0 degrees draft, the halves of the mold won't be able to separate, and that'll be a problem. Just some of, you know, as I said, many dozens of considerations for manufacturing for mechanical parts. This slide talks to a lot of details around design considerations for electronics. You might think that you're just putting, you know, a speaker and a battery and maybe some resistors and capacitors together on a circuit board to make the device that you have. But there's a lot of thought that needs to go in to selection of those components when you think about going into production of a system. Components have a lifetime typically, and so, you know, you do things like make sure you're not picking components that are hard to get, so their availability, their lifetime. There are standards around materials used in electronics. That's what ROHS stands for, Restriction on Hazardous Substances. That it relates to restrictions for use of lead, for example. Components can be derated if you look at the detailed data sheets. You know, resistors, capacitors, etc. Are often derated microprocessors as a function of, it could be voltage, current, temperature, etc. So the component selection is really important. The design of the circuit board itself is really important. When you get to a commercial product, there's regulations around what's called electromagnetic compatibility. So that refers to immunity of an electrical system from static discharge or electromagnetic energy, like, for example, static and energy from wireless transmitters and things of that nature. So there's a lot of, design for manufacturing that goes into those considerations. Protecting the circuit board with conformal coatings, for example, so sort of environmental protection from temperature and humidity and those kinds of things. I won't go into all of these details. There's a lot to think about just with respect to circuit boards. But cabling, cables are important when you're making a prototype. You're snipping the wires and attaching them yourselves. Getting into production, actually, the design of cabling is really important. Cabling can introduce a lot of noise into an electrical system, so there's things that you do with shielding and twisting and ferrites and things of that nature. And connectors, actually, you might not think twice about the connectors that you use when prototyping, but connectors, number one, they can be expensive and add a lot of cost, and number two, they can be a source of assembly and reliability problems. And so people put a lot of thought into designing the cabling system. We like to say wires are people too, and deserve appropriate consideration to how they are designed. Okay, just briefly, it's often the case that reliability problems crop up at production scale that you don't experience at prototype scale. So it's important to think about where sources of reliability issues can come from, whether it's the design, the parts that you pick, or how the device is manufactured. You try to anticipate that as much as you can. And as you start production, test to uncover those problems that you don't see at prototype scale. I just won't get into details here, but just briefly to mention that there are compliance requirements that have to be addressed as well that can affect how devices are designed. You want to make sure you're aware of requirements that are going to apply and design for compliance with those. Typically, you're going to take product that comes out of the pilot scale of production, and you're going to run that pilot product through the testing and reviews that are required to comply with applicable laws and standards. And then people often discount the challenges even when you've done all the stuff that I just talked about. Just getting a product actually into production is a huge effort. There's a lot of work that has to be done to engage a contract manufacturer. Let's assume you're not building your own factory and you're going to have somebody else build the product for you. You have to create typically what's called a procurement specification that defines what you want that contract manufacturer to do for you. You're going to be married to that organization for a long time, so you want to be smart about who you select. So you want to identify a couple, like buying a car. You don't buy the first one you see. Test drive a couple first. Get quotes from them, and select. And people select contract manufacturers based on different criteria that may be have different relative importance. Cost is certainly important, but location. You might want to have a manufacturing partner that you can drive to. That's not on the other side of the world. And there's other services that contract manufacturers can provide as well that's important to think about, like order fulfillment, servicing, field repairs, those kinds of things. Keep in mind that different manufacturers may have different constraints on their capabilities, and so it can often be the case that you think you're done with the design of your product, but you may need to make some tweaks to fit within the capabilities that a manufacturer can provide to you. And then once you've contracted with that manufacturer, you want to be thinking in terms of starting with a small pilot production run, where you're really scrutinizing the product that's coming out the other side to make sure that that manufacturer has established appropriate levels of controls around their suppliers, the production methods, how they're going to control the quality of that resulting product. Lots of testing you need to do here, and really scrutinize what they're doing to make sure they're giving you a good product at the end of the day. And oversight as things get ramped up, because it's always the case that something unexpected is going to happen. Something that we assume as designers is going to be straightforward to produce in manufacturing may not, that may not be the case. It always happens that there's issues that come up as you start to scale up and make more of whatever it is. You're gonna have issues that will need attention to resolve. So this process can take 6 months up to more, 9, 12 months in some cases. People don't often appreciate that lead time that's required to get through all of these activities.
So to give some context to it, for a simple device like the toy my students built, what would be a ramp-up production volume, would you say?
What's going to take the longest is tooling to make the plastic parts.
Mm-hmm.
Circuit boards, circuit boards can be manufactured with a fairly quick turnaround time. The plastics are the long pole in the tent. As you ramp up, you would typically make, I'm going to say, a pilot scale lot of, on the order of 50 to 100 kind of a thing. Different manufacturers are going to be, more or less suited to making, I'll say, lower quantity. If you have a device where you're manufacturing on the order of hundreds or thousands per year, that's a different kind of a manufacturing partner than you're going to need for a device where you're expecting to make hundreds of thousands or 1 million a year kind of a thing. So what's interesting in a lot of the work that we do in the medical field, many of those systems tend to be lower quantity. They're not consumer products. Their customers are hospitals. They're making hundreds or thousands of X-ray machines per year, and so that's a different kind of thing than a consumer device like a smartphone, where they're making hundreds of thousands or millions a year.